Let's cut right to the chase. You should write unit tests. I should write unit tests. Everyone should write unit tests. But I doubt this is new information. You've probably heard this before. From professors, coworkers, managers, read it in blog posts and articles, heard it in conference talks just like this one. But when you think about all the code you've ever worked with, all the code you've ever read, all the code you've ever interacted with, does it uniformly live up to this imperative? Is all the code you've ever written tested? How do we reconcile the fact that it's not the case, given that we all know this imperative? If we've all heard this before, why aren't we all doing it? And I would posit the reason for that is a mismatch in motivation. We've all heard this imperative, but do we really understand the full set of reasons we should write unit tests? Or is this imperative poorly motivated? When push comes to shove, when there's a deadline looming, or when something is really critical or really hard to test, maybe because we're not sufficiently motivated, we give up and we don't write unit tests. So I'd like to explore the reasons we write tests. I'd like to explore them against the backdrop of a bug I recently interacted with, a bug involving pcap files, which my company works with quite heavily. We capture pcap files, we reread and reprocess them, we rewrite them. We split them, sell them, entitle them, and distribute them. Fortunately for us, the pcap file format is quite simple. A global header containing some metadata telling you how to decode the remainder of the file, and then just a stream of records, where each record has a header and a payload, and the header gives you the length of the payload. Except that's a bit of an oversimplification. The pcap record header doesn't just give you the length of the payload, it gives you two lengths that appertain to the payload, the so-called original and included length. The original length is the number of bytes that were actually seen on the wire on the network. And the fact that there's another size beyond this suggests that something might happen to that data as it's recorded. The pcap standard allows packets to be truncated for the so-called included length to be less than the original length for data to be dropped on the floor. You might configure a maximum capture size, say, of 1,000 bytes and then receive a packet that's 1,400 bytes long. And so you write 1,000 bytes to the file, but you record those 1,400 bytes in the original length. And the fact we have this formulation, this possible mismatch, suggests that because we do so much work with pcaps, we have a model for dealing with this in memory, in our process. It should be noted that as an extension to the pcap standard, we also allow for padded packets to increase the size to have the included length longer than the original length so we can align structures appropriately in memory. And so we use utilities to deal with this. Because when we're processing the data, when we're actually looking at the bona fide data that was transmitted on the network, we only want to look at the original length number of bytes. We don't care about the padding when that happens. We just want what the peer sent. But then we remember that packets can be truncated. There might be fewer bytes in the original length, and we don't want to careen off the end of a buffer into undefined behavior, so surely the number of bytes we use in our processing should be the minimum of the original length and the included length. But when we write back to the file, when we rewrite that process pcap, we need to preserve that included length because it's in the header, because it's necessary for the reader to synchronize themselves against the file, because they need to know how many bytes they should skip ahead to get to the next record. But as I've gone through this, as I've talked through what the code on the slide does, you may feel uncomfortable because there's a typo on the slide. But I assure you, there is no typo on this slide. The typo is in the code itself, because this code has a bug. When we rewrite back to the file, we write the wrong number of bytes, even though we write the correct number of bytes in the header. And that leads exactly to that desynchronization that I was just talking about. On the left, we see the data as it originally existed in the original pcap that was emitted by the capture application. We can see the original length correctly denotes the information received from the network, and the included length correctly gets us to the next packet record capture header. But then on the right, we see the result of rewriting with the buggy code. The original length is still correct, but because we neglected to rewrite the padding, the included length now takes us past the next packet record capture header. This means that the reader becomes desynchronized. Because the pcap format is not self-synchronizing, they lose the stream irrecoverably. They start reading random bytes as though they're pcap record headers. They careen off into nothingness, yielding only corrupted data. But now that I've made you stare at that slide that seemingly had a typo, now that I've explained the result to you, surely the code is wrong by inspection. This is a simple fix, just one line, one value that needs to be changed. So surely we can just change it and move on with our lives. But this is a talk about unit testing. So surely the answer to that question is no. Surely we need to test this code somehow. And I'm going to put my money where my mouth is. I'm going to show you the commit that actually fixes this bug in our system. It describes the bug in detail, but at the bottom of the slide, you can see the files that were changed. You see that one line was removed and added to fix the bug, but that 150 lines of test code were added to ensure it works. And even if we understand the imperative, we write unit tests, that seems like a magnitude mismatch. Why do we need 150 lines to test just 2? Which brings us to the reasons we write tests, the motivation for writing a test suite like this. Let's start from the beginning. The first reason people will tell you when asked why they should write unit tests, they will say, I write unit tests to make sure my code works. And this motivation is reified differentially across the software development lifecycle. When you start out, when you're in the design phase, you use so-called test-driven development. You write tests which model your expectations before you even begin coding. Perhaps you write up your interface in a header and write a test suite against that, which compiles but doesn't even link yet. This has the advantage not only of giving you a goal to shoot for, a point when you know you're done, when all those tests pass, but it also makes you a user of your interface before you've invested any time in implementing it. Usability concerns drop out early. You can just change the interface rather than having to go through and do a bunch of complicated refactoring later. Then, as you move on to your actual implementation, you're going to learn more about the problem domain than you thought possible. Because the quickest way to learn about something is to try and write code that deals with it. You're going to discover sharp edges, edge cases, things you hadn't considered before. But unit tests are just lines in a source code. They're cheap and easy to write, so when you find these sharp edges as you're writing your implementation, don't just stare at the code you've written and convince yourself that surely it must address the situation. Just go and write a unit test that checks it. And then as you move on to the most long-lived part of the software development lifecycle, maintenance, you're going to get bug reports and feature requests, and each of these should be modeled in a unit test as well. Before you go and implement the feature request, you should change the interface and write a test that fails, and then only consider that feature request done when the test passes. When you get a bug report, you write a reproducing test, it fails, you make it pass, and you move on. But this formulation belies the true value of unit tests. When you get a feature request or a bug report, you're not just making one test that passed in pursuit of that goal go green. No, you want the entire test suite to go green. You are taking and you are integrating new knowledge about the problem domain against all of the knowledge that has been iteratively built up by all the developers who worked on this code artifact before you. Because writing unit tests is not just about making sure your code works. Writing unit tests is the process of systematizing information, of collecting all the data gleaned about the subject matter in a manner that can be automatically checked. You could go out and write documentation to transcribe all of that knowledge, but who actually does that? Who maintains that documentation, and who, when faced with a critical bug, actually opens up the documentation and reads the totality of everything that's ever been written about the component before they even begin? And even if they do all these things, they're just flawed human beings. They might misunderstand something. They might miss something in the documentation. Unit tests are automatically checked against every revision of the code. All of the effort people put into learning about the problem domain and adding to it is automatically integrated against the would-be solution at every step of the way. And if you don't systematize information in this way, you're going to encounter situations where you realize that's exactly what you're not doing. You're going to send Slack messages like this when you try and take some legacy component that's untested and port it to a new, better framework and try and capture it in a testable environment. You'll see some questionable code, some questionable branch, and you'll be unsure of whether or not it was added intentionally. You have no idea the scenario it was added to address. You stare at it and wonder if you have to preserve it. You resort to all kinds of complicated golden master testing to prove whether or not it's necessary to match up output with the past artifact. But this knowledge and information was at one point resident in someone who wrote the code. They understood the exact scenarios they were trying to address. They just didn't write them down. And we might say, well, they didn't test their code, but that's actually exactly wrong, which brings us to another motivation for writing unit tests, and that's the fact that the person who wrote this artifact originally tested the code, they just didn't unit test it. Because whether you write unit tests or not, you do test your code, you just do it differently. You write a throwaway executable where you ad hoc manipulate your interface and manually check the output to ensure it's what you expect. Then as you iterate on your development, you change that ad hoc executable and you lose sight of the important cases you captured in the past. Maybe you get a bug report and you painstakingly synthesize a reproduction. You bring together input and configuration files and an exact binary in an exact environment, and you see a reproduction of the bug, fix it, and then see that reproduction disappear. But then all of the information you wrote about the reproduction and the scenario just vanishes into the darkness of your bash history. It's no longer easily accessible for future people maintaining the code to interact with. The knowledge and understanding that you have about a possible problem in the problem domain is lost. But you still spent time synthesizing it. Which brings us to the last motivation I want to put forward for unit testing, and that's that unit testing actually makes you measurably more productive. If you spend 3 hours investigating a bug and 30 seconds changing the one line of code that causes it, and you just commit that one line through, you've captured 30 seconds of the last 3 hours and 30 seconds of work that you've done. Why are you throwing your time away? You're writing tests anyway. Why not just write them in a form that can actually be committed through? Why not capture the fullness of your output? Why not actually get something from the hours you spend in front of your computer? Why not transmit them forward to be exponentially levered up by all the developers who come after you? Which brings us back to those 150 lines written to test just 2. Except that is exactly the wrong way of putting it. I didn't write 150 lines to test 2. I wrote 150 lines not knowing what was wrong with the code at all. I got a bug report. I figured out a plausible reproduction. I put together a unit test that took a padded packet, wrote it to a file, reread it, and saw that the reread packet was corrupt. Saw that we had desynchronized from the stream present in the file. Only then, once I'd seen the reproduction, once I'd found a flaw in the software artifact, did I go looking for that 2-line solution. It was only through serendipity that it was only 2 lines, not 200. But when I got to the end of the road, I wanted to capture all of the work I'd done. I wanted to capture that reproduction and commit it through. Those 150 lines were what led to the 2 lines, not the other way around. Because even if I'd found the bug by inspection, surely I would have done a full end-to-end test, and surely I want to capture that context as well. I don't want to just put together an ad hoc bash command, run it, say that I've succeeded, and then just commit through 2 lines with 10 lines of test code. No, I want to capture the fullness of what I've developed. I want to capture the fullness of the scenario in which this possible problem in the problem domain emerged. But now that we understand why we should unit test, that brings us to the next question. How do we unit test? There are many things that is asserted cannot be tested, or are difficult to test, or are not worth testing. When our principles run into this obstacle, what are we going to do? But in the formulation I laid out before, there's already such an obstacle. I said that I wrote something to the file system and then read it, which means we need to rationalize the file system, because the file system is a pernicious global shared with all processes on your system, or if the file system is network attached, with all users on your network. So we need some structured way of obtaining a private corner of the file system we can interact with as though it is a local. We need some way to get ourselves an anonymous temporary directory in a way that is fail-safe. And that's exactly what this example function on the slide does. I simply pulled the signature of a function out of a proprietary database we maintain. In production, of course, the user would give you a path. You'd open a real bona fide path in the file system, and you'd interact with it, and everything would be published out and shared. That's the whole point of the database. But when we write our unit tests, we need an easy turnkey way to get ourselves a completely private, completely clean copy of a brand new database. And so we call this, we can build up a reproduction therein, knowing we're shielded from everyone else using the system. We can examine the leftovers, knowing that no one else has contributed to it, that we're completely isolated. And then as we run off the end of our test, we release this handle, the directory is cleaned up, and the next test starts completely fresh. And if you don't think this is worth it, if you think you can work around having to write routines to get you completely private corners of the file system, you're just going to end up writing this commit message. You're going to end up picking some well-known path that you know for a fact that no one else uses. and then someone else is going to run the unit test suite on a shared machine at the same time as you. Someone's going to increase the level of concurrency in your CI environment. Someone's going to decide that they really, really like your test. They're going to copy and paste it and use it as a template for their own, and they're going to forget to change that path. Which brings us to a bug this technique was important for solving. Which brings us to a bug in a component I wrote which atomically publishes files, fully formed into their final destination. This is very important when you're using the file system as a means of communicating between distributed processes. You don't want any risk they can read the file half-formed. To achieve this, I used the rename at2 syscall with the rename no replace flag. At least I did originally. I ran a test suite against ext4. The test suite passed, and I shipped it. But then our deployment environment was against NFS, which, whether or not the kernel supports rename at2, does not support rename no replace. And so I ended up with the error on the slide. And this sort of bug is the one that many people would fix by inspection and conversation. They'd fix it, and then in code review, they would painstakingly explain how the bug is actually fixed by this change with no proof thereof. But this commit message actually attests to the fact that I didn't do this, that I added a new unit test, and that I managed to make it fail somehow and reproduce the bug, and thereafter made it pass. And that unit test is this one which makes use of the component to publish a small file and simply ensure that it can be reread. But there are multiple interesting things about this test. The first of which is the fact that I'm reaching into a detail namespace in order to test something. I'm not manipulating the high-level component to try and induce it to exhibit this small targeted piece of behavior. Because I suspected this component originally, I refactored the code to take that function from a inline namespace in a CPP file and expose it in the header in a detail namespace. The detail namespace is a contract with my users that they will never use this, but I, the author of the component and the author of the tests, am more than welcome to do so. Then, after that, I need to get a private corner of the file system, and that is exactly what this tempter variable does. Injected into every single test we run, it lazily expands to a path of a newly created empty directory. You can go off and use that directory, put files in it, read files from it, and then as you run off the end of the test, it's cleaned up. All the files and the directory are deleted. Subsequent tests that make use of this will get a completely new, completely fresh directory. But I already mentioned that this component was working against ext4. I mentioned that the problem was only against NFS, and very unfortunately, the temporary directories this tempter component spit out are not backed by NFS. They're always backed by ext4 in my development environments. So having written this test and failed to reproduce the problem, I needed some way to get a temporary directory against NFS. Maybe that should be a bona fide part of our test suite, a bona fide part of our continuous integration environment that I can specify the exact file system I want my temporary directory to be backed by. But that's a much larger ask than fixing this small issue that's critical because we want to get this component into production. And so what I did was I simply shadowed tempter with my home directory, which is very unfortunately backed by NFS. This test failed immediately. The rest of the test suite was fine, but this test failed. I went and implemented the algorithm I described on the preceding slide. I reran this test, and it passed. I could commit this through minus this one line. I'd obeyed my principles as far as I could take them until I get access to a component that allows me to, in a turnkey fashion, get a temporary directory backed by NFS. But I still captured the fullness of my output. I still managed to improve the software artifact by making this function easier to test in isolation going forward. I encoded the fact that it could be a source of bugs and made it readily accessible for people in the future who want to fix those bugs. But I also pulled something out and put it in a detail namespace, which can be controversial. But I'll posit that's actually good for testability. Often people will write a component on top of 2 or 3 genuinely difficult to test functions. Maybe they interact with some driver that all your machines don't have, or some piece of bespoke hardware that's only present on a few machines in the company. And they'll say that transitively, because the code is infected by these untestable calls, they get away with not testing any of it. All of it is consigned to manual, painstaking testing, which is liable not to be implemented perfectly each time. And that's exactly what happened in this scenario. We were playing bug whack-a-mole with this component, manually fixing one bug and verifying we'd fixed it, only to regress several others. We went back and forth until finally I became frustrated with this status quo, took the entire component, refactored it into a detail namespace, and made it just templated on invocables for which you could provide an implementation of the untestable functions. Then my testing harness was able to fully mock and manipulate the entire thing and bring all the bugs that we'd been fixing under test. But to the astonishment of no one, who understands the importance of unit testing, this is not all that I accomplished. Because believe it or not, this old legacy component, once refactored and made testable and tested, didn't just have the bugs we thought it had. It had still other bugs which had not yet been discovered, which that testing exposed. And so I was not just letting out my frustrations that people weren't writing unit tests the way they should. I actually contributed value and eliminated reputational risk for my company by writing these unit tests. I headed off bugs that no longer had to be embarrassingly reported to us by users. I addressed them before anyone but me even knew they existed. But we were talking about files. So here's a perfectly plausible file, 12,288 bytes long. You might say that it's exactly 3 typical Linux pages long, which of course immediately brings up the specter of the fact that you are, of course, more than welcome to memory map it into your process. There's nothing wrong with that. But as I mentioned earlier, the file system is a global. It's accessible to everyone on your machine. Someone can just wander by and manipulate this file despite the fact that you have it mapped into memory. Maybe they open it. Maybe after they open it, they decide that it's altogether too long. They call ftruncate thereupon, and now suddenly your 12,288 byte file is only 8,192 bytes. But you mapped 12,288 bytes into your address space. You thought you could access all 12,288 bytes. What if you go and you try and access that final page? The final page that's no longer backed by extents in the file. What's going to happen to you is that your process is going to receive SIGBUS. The default action for a SIGBUS is to terminate the process. But this is wildly inappropriate for the situations wherein we use memory map files. We use memory map files to export telemetry information, and while that telemetry information is important, it's not as important as the production runs that are exporting the telemetry information. Just because someone's script can't synthesize a unique file name, just because there's some collision or someone clobbers the file, doesn't mean the entire production run should come crashing down. And so we tried to write a component that could solve this, that would solve this by replacing the files. Instead of opening them and truncating them, we want to actually replace them. Leave the inode of the previously existing file around, but unlink it from the file system so it can be used by whoever has a descriptor open there too in the background. And then replace it with a new inode that we can use actually linked into the file system. Unfortunately, the person who authored the code that you see on the screen didn't understand that ocreat and otrunc combined together don't actually give you this effect. Sure, that will create a new file if it doesn't already exist, but if it does exist, it will just open the file and truncate it to 0 bytes, which is exactly the behavior we're trying to avoid. And so invariably, this behavior manifested itself. Something died with a SIGBUS, and someone thought they would go ahead and fix the problem, or should I say, fix the problem. They wandered by and decided that the correct solution was to simply blindly unlink the file before they tried to open it. That way, the file would be unlinked from the file system, the inode would carry on if someone had a file descriptor open there too, and they could proceed to create a brand new file in its place. Unfortunately for them, modern computers have many processes which can run their operations interleaved, and so it's completely plausible that process A enters this function. It unlinks the file, but finds nothing, which is totally fine because no one checks the return value from unlink, and so that E exists, that E, no ent, will be completely discarded. Then they proceed to open the file. But of course, this can take some measurable amount of time. It's not instantaneous, and so nothing is stopping process B in the meantime from entering the function and attempting to unlink exactly the same file. But of course, it won't find it because process A hasn't proceeded far enough yet. And so it unlinks nothing, and then it proceeds down to try and open the file as well. In the meantime, process A actually makes some forward progress. It actually creates that file, and it gets a descriptor there too. But why would it be opening the file if it didn't want to use it? Surely it wants to allocate some memory therein and map it into its process, and so it enters the function down below and does exactly that. It truncates the file to make it longer, and then maps that newly allocated memory into its process. But as it moves to return and use that memory, process B finishes the call to open. It falls out of the call to open, and having found a file that already existed with some extents allocated into it by process A, it truncates it to 0 length, which causes process A to end with a SIGBUS, which causes exactly the scenario we were trying to avoid. And this is an instance of an entire class of bugs which we refer to as TOCTOW, time of check to time of use. In some sense, the unlink was a check. We established that some predicate was true, that the file didn't exist. Later, we used that information in the correctness of our algorithm. We relied on it for that call to open to achieve the effect we desired. But between the time we checked and the time we used, the truthiness of that predicate was liable to change. Someone else could have created a file introducing a bug. But how can we possibly induce this behavior? How can we possibly induce this situation so we can bring it under test and prove that we've actually fixed it? Surely we can fix this by conversation. We can just change the algorithm and write a lengthy commit message describing it and convince our coworkers in code review that we've actually addressed the bug and hope that iteratively across the software development lifecycle, everyone else who stares at that code doesn't regress the bug in their naivety and lack of understanding of this exact scenario. But as we stare at the commit message on the screen, we notice the commit message actually attests the opposite. It attests that it reproduced this scenario in a unit test and verified that this fix actually achieves the desired outcome. And the way it did it is like this. It simply spun up 100 threads and had all of them create 100 files, and then map in 1024 bytes therefrom, and then access those bytes in some way. And this may seem hokey, but what's the alternative? What's the other way of bringing this under test? Going to the fix by conversation where I don't demonstrate the defect at all and I just convince people through conversation that it exists? Where I blindly modify the code for no reason because the passingness of all the unit tests didn't fail? They passed before and they pass now, but I changed code for no reason? No, it may seem hokey, but it actually works. This reproduced the bug every single time I ran it against a buggy version of the software. It crashed and ended with SIGBUS each and every time. Then when I updated the algorithm we used in accordance with the commit message I just showed you, it passed every single time. It was included in the commit. It was merged to master. It runs in CI every single time CI runs, and it passes in CI every single time. But we can take the complexity of this issue and we can lever it up. We can move on to implementing something like an algorithm called double-checked locking. We might want to lazily initialize something in a thread-safe way, and so we can use this technique to do so. This is actually in some way or another burned into the C++ standard since C++11, which introduced so-called magic statics, which lazily and thread-safely initialize themselves. We can implement this in the following piece of code. We have some database file that has some metadata file next to it in the file system. We want to lazily read that metadata when someone needs it, but we want to cache it so it doesn't need to be reread by every consumer thereof. Something like double-checked locking. But note that in the middle, to release the lock while we perform an expensive file system operation, we release the lock and then reacquire it, which unfortunately means we leave ourselves open to a bug. Thread A can enter this code and acquire the lock and then find that the metadata has not yet been loaded and move to proceed with the initialization we want to lazily perform. And so it moves on to perform that expensive file system operation, but in so doing, it drops the lock to ensure that other people can acquire the lock and thread safely process this object. Thereafter, thread B is more than welcome to enter this function, acquire the lock, and also find there is no cached metadata. Then it too proceeds to perform that expensive file system operation. Some of you may be thinking that this is a bug on its face, but that's not necessarily the case. Maybe it's a slight performance regression, but if thread A and B have some protocol to work out whose loaded copy of the metadata is canonical and resolve that, this is a benign race. Sure, you might perform 2 operations against the file system, but if correctly resolved, it's no problem. Unfortunately, this code does not correctly resolve this situation. As thread A makes further progress, it acquires the lock and moves to install its metadata in the now empty cache. But in the meantime, thread B also finishes loading and goes to acquire the lock. The one thing about this that does actually work is the guard actually does guard the access to metadata, so thread B has to wait until thread A proceeds. It proceeds and returns a reference to the unique pointer that it just populated, as you can see from the function declaration. After it does so, thread B is immediately free to make forward progress because leaving the scope causes thread A to drop the lock, and so thread B can move in and reassign _ metadata. And there are actually 2 issues here that get more concerning as we explore them. The first of which is just a bog standard data race. Because we return a reference to the pointer, thread A may be reading from it while thread B is writing to it. This is a standard data race, undefined behavior in C++. It needs to be fixed somehow. It needs to be fixed by only having simultaneous readers or by having a lock and having only one writer. But the more concerning issue here, The reason why this bug is so notable to me, the reason why it occupied months of my life, is because of the fact that it has a use after free in it as well. It's overwhelmingly more likely that thread A will get a reference set pointer and then go off and start using it than that it will actually be a race on the pointer. And if it uses it, it's going to descend the configuration tree to try and deserialize it. It's going to walk that indirect tree. But as it does that, behind the scenes, the bug is manifesting itself. Thread B is assigning to that cached unique putter, and we all know that when you assign to a unique putter, the current pointee thereof is deleted. So as thread B attempts to traverse and parse the configuration structure disappears out from under it. Undefined behavior, use after free, which generates insanely unhelpful core dumps that make you believe that your serialization code is at issue rather than the locking. But this has a core difference between the previous bug. The previous bug was idempotent. We could simply spin in a hot loop and exercise the code over and over again, and the race condition could manifest itself anywhere. But this is lazy initialization. It's performed once. If the initialization is already performed, there's actually no bugs in the code I've shown you. It actually works when you access the cached value. It's only the first initialization that's problematic. So we can't just take the technique we used before and use it verbatim. We need to make an adjustment. We need to make an ad hoc implementation of something like C++20's barrier. The reason I don't just use barrier here is because this code was originally written for C++17, not C++20. Rather than spinning up a bunch of threads and having them spin in a hot loop trying to reproduce the bug, we spin up the threads but have each of them wait just above that problematic call to metadata, just above where they would populate that metadata and perform the problematic operations. Only once we've created each thread and we have an army of threads waiting to race with each other do we release them and allow them to fall into metadata. Each of them takes their paths to that function and records the pointer they get back. And then we check to ensure that each and every pointer is the same, because the failure modality is returning different pointers, returning pointers to different structures and having them be variously clobbered by one another. But we can lever up this even further. We can find even more obscure bugs to examine. Let's say we're trying to write something like a concurrent queue. Something that allows us to communicate between threads, allows us to move blocks of elements from a producer to a consumer. If you look at this slide, it looks fine. You see the needful synchronization primitives, you see the operations you would expect. At first audit, this code seems fine. But let's consider what happens when you try to pop from it. Maybe you try to pop from it, and the block you previously acquired from the producer has been exhausted. And so you take that if output exhausted branch, you acquire the lock, and then you need to move to interlock with the other thread so you can obtain a block of data therefrom. You pass in a reference to your unique lock as an attestation that you hold the appropriate synchronization primitive. And as you move to interlock, you find out that unfortunately, the producer is not ready for you. They're not suspended, so you need to wait for them. And so you call await and you pass in that unique lock as an attestation that you hold the lock. And then you set suspended to true so that the producer knows that you're waiting for it, and then you go to sleep on a condition variable. You await its signal for you to proceed with further processing. Once you awaken from your sleep, you're going to return from await into interlock. You're going to turn from interlock into pop, and then you're going to assert that the output is not empty. And surely it's not empty, because surely the producer signaled you that they had left some output for you to consume. Surely that is the reason you woke from your sleep on the condition variable, not the fact that every single condition variable implementation I've been able to find reserves to itself the right to spuriously awaken you for no reason at all. But this is just implementation latitude. Implementations are allowed to do this, but there's no requirement that they spuriously awaken you in any particular situation, even though every single implementer reserves the right to do so. So how can we possibly induce this scenario? How can we induce a spurious wake-up when we aren't even guaranteed that our implementation ever emits them? And as we ponder this question, as we peruse the text on the slide, we notice something. That commit message makes an attestation that that's exactly what it does. It adds a unit test which reproduces this scenario, which brings this flaw under test. And the way it does so is it leverages the fact that the mailbox is parameterized on a threading package which provides the exact types of synchronization primitives it will use internally. We don't need to rely on when the implementer actually spuriously awakens us. We can inject an implementation that spuriously awakens us. then we can test our behavior in the presence of such a condition variable. But as we think about it, as software engineers, as people who are one step removed from lawyers, we realize that if you're allowed to spuriously awaken someone when they wait, that means that you're allowed to spuriously awaken them every single time immediately when they wait on you. A valid test implementation of a condition variable does absolutely nothing other than have the required functions. But if you've ever interacted with stood condition variable, if you ever used the patterns that come with it in C++, you realize that the fact that we used the unary overload of wait in the first place was a code smell for exactly this purpose. For this reason, C++'s condition variable actually comes with a binary overload of wait, so surely our mock should provide that so our new code can leverage it and be correct by default. But as we think about this, if the requirement of our new design is that it be correct by default and use the modern patterns, and if it's a requirement that our code compile against this mock in order to be merged and shipped, why do we provide the latitude for the implementation to do the bad thing? Why don't we just say that our mock doesn't have the unary version of wait at all? Now our implementation needs to not only be correct in the face of the unit tests we're actually executing against it, it needs to be structurally correct because it wouldn't compile if it used problematic functions on the condition variable. But this is not the end of the story. When I inherited this component, it was untested. When I pulled the thread of this one bug, I discovered a cascade of bugs which I had to fix by restructuring the entire class. And when I committed it through, it passed all the unit tests that I had written for it, but no one else had ever written any unit tests for it. They had requirements they understood about the problem domain which they had failed to systematize. There was information they understood that they weren't transmitting to me as I tried to rescue their horribly buggy component. And one of those requirements that never occurred to me was the fact that the original design was for this component to be tolerant in the face of synchronization primitives which throw exceptions as a means of ad hoc transmitting thread interruption between threads. If a thread has been interrupted, the synchronization primitive would throw an exception. I didn't design the component with this in mind. I put no except in the proper places, and so when I tried to do production deployment runs with it, occasionally during shutdown, stood terminate would be called. I needed to adjust my implementation to be safe in the face of exceptions emitted by the synchronization primitives. I needed to provide the strong exception guarantee in the face of exceptions emitted thereby. And that is exactly what this commit message attests that I did. I tested the component to ensure that it correctly tolerates providing the strong exception guarantee, exceptions thrown by synchronization primitives at every single step of the operation. To do this, I leveraged a technique that I learned about in a cppcon talk I attended years ago, although I unfortunately couldn't find that talk to cite it. What we're going to do is we're going to provide a throwing condition variable implementation, which throws a synthetic error after a certain number of operations has been performed. The exact number of operations which have been performed can be customized. We see we have that synthetic exception type, and then we have a function that allows you to thread safely access the global throws after count. Once this count is exhausted, we throw an exception from the next operation that is performed, which is exactly what maybe throw does. It accesses the throws after count, it checks to see if it's been exhausted, and if it has, it emits a synthetic exception and resets the counter to infinity so we can proceed with operations with no further exceptions. Otherwise, it simply decrements the count. Moving on to the bottom half of this class, we arrive at the most important function, loop, which takes some operation we wish to perform against something parameterized on this threading package and repeats it until it doesn't throw a synthetic exception. It repeats it because we want to verify the strong exception guarantee. We want to verify that on the emission of an exception, it's safe to repeat the operation. We also note via out parameter that an exception was thrown. Then we simply have a setter for our global throws after count, and we have an implementation of condition variable, which does everything stood condition variable does, except sometimes it throws when requested. Which moves us on to actually writing the test that verifies we're providing the strong exception guarantee. Writing a unit test which loops from throws after equals 0 all the way up until no exception is observed, after which we can be sure that every single point which could have thrown an exception has thrown an exception. We move down the slide, we create a mailbox, and we spin up a worker thread which just goes and pops things off the mailbox. But it doesn't just pop them off the mailbox, it pops them off the mailbox inside of our loop function, so that operation will be repeated when a synthetic exception is thrown, and the fact a synthetic exception was thrown will be recorded. Then we handle the exception that indicates we're finished processing and record all other exceptions so we can inspect to make sure that didn't happen. Moving on, we set up some cleanup code so when we exit the scope, we will ask the consumer to finish. But again, we do so inside the loop function. We repeat this operation until it doesn't throw to verify we have the strong exception guarantee. Then in the foreground thread, we simply loop from 0 up to 100, and we push those elements into the mailbox to be consumed by the consumer. But one last time, we use the loop function. We're verifying here as well, we're providing the strong exception guarantee. As we reach the end of the function, we're going to expect there were no exceptions in the run, and then we're going to loop through the same numbers again and ensure that they were produced in the exactly correct order. This will catch issues where we don't provide the strong exception guarantee, where we allow the operation to be repeated, but we corrupt its content so we don't record the exact sequence of values we expect. Then at the very bottom, if we went through an entire run of the test and didn't throw an exception, if we've exercised every location whereat exceptions may be emitted, we end the test. And we're done. But while all of these are interesting, these bugs are interesting, and the tests therefore are interesting, it's all still local to the machine. I still control the entire machine. I control the entire environment. What about testing things over the network? Fortunately, I actually gave an entire hour-long talk about how you should write testable C++ networking code. So if that's interesting, you can go and watch that. In the meantime, I'm going to skip by that layer of analysis and say, what if we want to go even more global? What if we want to access the cloud? What if we want to write a C++ application that interacts with S3, creates and deletes, and manipulates keys and values therein? What if we want to do so by using a pair of C libraries, libs3 and libcurl, which aren't exactly amenable to modern testing techniques? The way we're going to do this is we're going to do it exactly the same way we did for the file system. We're going to take that global and we're going to rationalize it. We're going to use something called local stack to provide ourselves our own private cloud, our own private instance of S3 that we can manipulate and work with independently. A Docker image you can pull down and spawn into containers, each and every one of which is an independent cloud with its own independent S3 provider. Our CI pipeline integrates this. Every single CI run gets its own local stack container, its own private version of the cloud, and how to access it is injected into the run via environment variable. Not only this, but part of our unit test data repository is mirrored into that local cloud before the tests are allowed to run, so developers can be confident that every single time they write tests and interact with S3, they get a consistent environment. They can make mutating changes to S3 knowing that at the end of the CI run, that container will go away, that local copy of the cloud will no longer exist, and the next run gets a fresh copy. And maybe that sounds too good to be true, and that might be because it is. Nothing is perfect. When we went and integrated against a certain version of local stack, we discovered that it really didn't like when we connected to it and used HTTP 2. It would exhibit all kinds of weird errors. We had spurious failures in CI that weren't linked to any particular bug. It was extremely obnoxious. Fortunately, libcurl lets you opt out of its opportunistic use of HTTP2, so we can force it to only use HTTP 1.1. But in order to achieve that, you actually have to manipulate the easy handle that's associated with the connection. But we're only using libcurl transitively via libs3. And as we received libs3, it didn't actually allow this pattern. It didn't allow us to obtain an easy handle along with the association with the request the easy handle was being used in pursuit of. And so the reason there were 2 bullet points for libs3 on the preceding slide where I introduced the libraries is because we actually have a fork of libs3 that we update and maintain. We extended it to support exactly this pattern. We maintain that copy of the library to keep it in alignment with the modern usage patterns we want to pursue. But this talk isn't about libs3. This talk isn't about S3, it's about testing. So where are the tests? But first, I need to introduce you to one more feature of our S3 C++ stack. The fact that we actually allow users on a per operation basis to enable libcurl verbose mode. So when they're trying to debug some problem in production, they can just set a configuration value and see a complete verbose log of what's going on behind the scenes. But this kind of raises the same question. How can I test the fact that HTTP2 is being used? It's, after all, between the library and the network. And how can I test the fact that verbose output is going to standard error, another pernicious global? The way we're going to achieve that is by writing exactly this test. We're going to enable both of the options that we've just reviewed, and then we're simply going to list the objects in a bucket. But of course, we're going to do this with a mock S3 object in scope. We're then going to pull out everything emitted to S3 and verify it's not empty because verbose mode is on. Verify that it does not contain the substring HTTP/2 because libcurl actually outputs all of the headers of the requests it makes when it's in verbose mode. So if that substring is therein, it means that HTTP2 was used in contravention of our request. But what's interesting about this test is not the test, it's this. It's the fact that we attest that we're mocking out a global. We're mocking out standard error in a scoped way. We've rationalized one more problematic thing that gets in the way of unit testing. The implementation of that mock S3 is the most interesting part of this. We have a cleanup function which uninstalls our mock by doing some dupe2 magic and closing some file descriptors. And we have two file descriptors we're going to keep around. The read end we can pull the contents of S3 out of, and an FD underscore whose purpose will become clear in a moment. Then our constructor gets everything started. We duplicate the standard error file node into that FD underscore, and then we do a bunch of operations that create pipes and dupe things around so that whenever someone uses standard error anywhere in the process, they're seamlessly captured by the right end of our pipe. Then the read end of our pipe is just sitting there waiting for us to pull the contents of standard error out for inspection in our unit tests. And the reason I'm glazing over this implementation so thoroughly is that it's much more easily understood visually. It's much more easy to understand what's going on here if I show you a diagram. So here is the state you find yourself in when you start the constructor. The standard error file number points to the file description of standard error. Note that descriptors and descriptions in POSIX are different. A descriptor is just a handle to a description. Thereafter, we use dupe on the standard error file number to get another reference to the standard error file description to make sure that it doesn't go away as we manipulate standard error file node going forward. We create FD underscore, which also points to standard error. Then we call pipe and create a pair of pipes, two more file descriptors and two more file descriptions. But then we use dupe2 to change the meaning of standard error file node to point to the right end of the pipe. Now, whenever anyone writes to std file node anywhere in the program, that well-known global, we are capturing everything they write to the right end of the pipe, but we're also keeping the original standard error around using FD underscore. We, of course, keep read underscore to ourselves so we can privately read out everything that was written to standard error during our test. Which just leaves that cleanup underscore function, which leaves us getting back to the state we were in before we entered this component so the environment is put back to where it was. The way we achieve this is we first take FD underscore and apply it onto the standard error file number, which frees the last reference to the right description and makes it go away. Thereafter, we just need to close the two descriptors that we have open, and we're back to exactly the same state we were in when we entered. Which just leaves us pulling out the data that was written, which leaves us writing that get function, which takes a string and simply reads into it repeatedly until it exhausts the data and returns it. But it doesn't just return it. Before it returns it, it actually eagerly performs the cleanup. Why would it possibly do this? Well, when you think about the case in which this is going to be used, we're going to call get and we're going to return a std string. The user is probably going to inspect that string. They're probably going to assert about qualities of that string, and those assertions might fail. Their expectations might not hold. If their expectations don't hold, the unit test framework is probably going to write information about that failure to standard error. And if we're still capturing it, then we're going to suppress the visibility of those error messages to the user. This is actually something that I encountered myself the very first time I used that, and this is the exact reason that second from last line is there. We release standard error before we give the string back to our user, so our user's assertions are properly written to standard error. The real one, not our mock one. But as I said in the title of this talk, these bugs are fantastic, and these tests are fantastic. What about this function? What if I just want to write a function that takes in a fixed size buffer and trims off all the nulls to get me the actual string that's inside it? Something you find yourself doing very commonly when you interact with UDP market data protocols, for example. Surely someone like myself can just write this function without adult supervision. Surely I know exactly how to implement this function. I don't need to test it. I can just write it. It's trivial. I can put it off in a CPP file with internal linkage, and there's no need for me to exercise it. But what if I told you that I have actually written this function, that I took a stab at writing it myself, and this is what I ended up with? When I wrote the unit test suite that verily I wrote for this function against it, UB Sanitizer came and told me, your function has undefined behavior. because somehow or another, writing this tiny little function, I got distracted, or I was just feeling absent-minded, and I didn't put in a return statement. So control just flowed off the end without returning anything, undefined behavior. Now imagine I'd taken and actually put this in a CPP file with internal linkage. I just used it as part of my implementation, taking for granted the fact that surely I can write this function flawlessly. It's completely trivial. Now imagine in the high-level testing of that component, that code path was never taken. I never learned this had undefined behavior. It got released to production, and I had to deal with bug reports and production crashes when that branch was unexpectedly taken. I would have thrown off my entire day, my entire vibe for the whole week by dealing with a bug in a panic that I could have avoided by just writing this. Is the time saved by not writing that worth it? Worth it for the interruption and disruption to your day and your life and your week? Being woken up in the middle of the night, spending a Friday fixing a bug? No, we should just write the unit tests, which is the thought I want to leave you with. Everyone should write unit tests. Not because I stood on a stage and told you I should, but because you understand the reasons why it levers up your workflow and improves the deliverables that you produce every day at your job. Once you understand that imperative and the reasons that motivate it, you will write the unit tests. It won't matter that it's difficult. Where there's a will, there's a way. When you understand you must write tests, you can't just accept the fact that this is untestable. You'll find a creative solution just like the ones I presented to you in this talk. Because at the end of the day, no functionality is too trivial to be tested. Nothing is so simple that a flawed human can't mess it up. No one is so elevated that their work isn't worth checking, especially if those checks are automatically evaluated at every step of the life cycle, and you can proceed safe knowing that all information that anyone has ever learned about your problem domain is modeled in the solution you're delivering today.